Ich habe hier noch einen Film.
Today, you and I are going to get into divergence and curl, two central ideas from vector calculus. But if you'll indulge me, it's what fluid flow have to do with electric potential, and what do both of these have to do with complex numbers? If you want to understand what's going on here, you need to be comfortable with two central ideas from vector calculus, divergence and curl. Now for me, writing this, scope creep event.
So, beides haben wir gehabt, ne? Divergenz und Rotation. Divergence und Curl im Englischen. Ja, formell sieht es ähnlich aus, allerdings eine unterschiedliche Operation. Einmal ist hier ein Skalarprodukt und hier einmal ein Kreuzprodukt. Nochmal die Frage, was macht die Divergenz? Die gibt mir an, wie stark etwas nach innen oder nach außen geht, auf wie viele Quellen ich habe oder wie stark die Quellen sind. Und das gibt mir an, wie stark die Wirbel sind. Und jedes Vektorfeld ist zerlegbar in einen Divergenz- und einen Wirbelanteil. Das sehen wir jetzt hier.
Actually turned into a sort of scope meiosis as the section giving the background grew out into its own video. And, well, here we are now. Anyway, you might be wondering, why am I spending your precious minutes and my precious hours to tell you about this, rather than just jumping straight into the actual topic? Well, individual topics tend to be less enlightening than the connections between them. And learning about divergence and curl runs the risk of feeling kind of arbitrary if it comes across as just some other thing that you do with derivatives. But there's something more exhilarating while learning it, if from the get-go, you have some awareness for just how far-reaching these ideas will be. To make sure we're all on the same page, let's begin by talking about vector fields. Essentially, a vector field is what you get if you associate each point in space with a vector, some magnitude and direction. Maybe those vectors represent the velocities of particles of fluid at each point in space, or maybe they represent the force of gravity at many different points in space, or maybe a magnetic field strength. Quick note on drawing these, often if you were to draw the vectors to scale, the longer ones end up just cluttering up the whole thing. So it's common to basically lie a little and artificially shorten ones that are too long, maybe using color to give some vague sense of length. Now in principle, vector fields in physics might change over time. In almost all real-world fluid flow, the velocities of particles in a given region of space will change over time in response to the surrounding context. Wind is not a constant, it comes in gusts. An electric field changes as the charged particles characterizing it move around.
Hier kann man nämlich sehen,
Electric
wie
field
die
changes.
einzelnen Ladungen sich bewegen und aufgrund der Ladungen, die sich bewegen, sich entsprechend auch das elektrische Feld ringsherum verändert. Und dieses elektrische Feld, was man ringsherum, diese Änderung, die wir hier in den Pfeilen sehen, die kann man auch messen oder kann auch hinterher induziert werden oder je nachdem, wenn die Ladungen sich relativ schnell bewegen, kann man auch damit Antennen bauen und dann ist das im Vakuum ein elektrisches Feld, was dann seine Polung ändert und anhand der Signale, die man dann sendet, da gibt es ja verschiedene Verfahren, werden Sie in Nachrichtentechnik wahrscheinlich nochmal mitbekommen, kann man dann über Funk Informationen übertragen. Passiert wo? Zum Beispiel wenn Sie mit WLAN unterwegs sind oder wenn Sie einfach so mit Ihrem Handy unterwegs sind, ohne WLAN und Funkempfang haben. Das sind elektromagnetische Wellen, die sich ständig ändern. Wir haben momentan nur ein Standbild. Ja, das habe ich inzwischen jetzt ja auch leider gesehen. Warum
as
auch
the
immer das
charged
passiert
particles
ist.
characterizing it move around. But here, we'll just be looking at static vector fields, which maybe you think of as describing a steady-state system. Also, while such vectors could in principle be three-dimensional, or even higher, we're just going to be looking at two dimensions. An important idea, which regularly goes unsaid, is that you can often understand a vector field which represents one physical phenomenon better by imagining what if it represented a different physical phenomenon? What if these vectors describing gravitational force instead defined a fluid flow? What would that flow look like? And what can the properties of that flow tell us about the original gravitational force? And what if the vectors defining a fluid flow were thought of as describing the downhill direction of a certain hill? Does such a hill even exist? And if so, what does it tell us about the original flow? These sorts of questions can be surprisingly helpful. For example, the ideas of divergence and curl are particularly viscerally understood when the vector field is thought of as representing fluid flow, even if the field you're looking at is really meant to describe something else, like an electric field. Here, take a look at this vector field and think of each vector as describing the velocity of a fluid at that point. Notice that when you do this, that fluid behaves in a very strange, non-physical way. Around some points, like these ones, the fluid seems to just spring into existence from nothingness, as if there's some kind of source there. Some other points act more like sinks, where the fluid seems to disappear into nothingness. The divergence of a vector field at a particular point of the plane tells you how much this imagined fluid tends to flow out of or into small regions near it. For example, the divergence of our vector field, evaluated at all of those points that act like sources, will give a positive number. And it doesn't just have to be that all of the fluid is flowing away from that point. The divergence would also be positive if it was just that the fluid coming into it from one direction was slower than the flow coming out of it in another direction, since that would still insinuate a certain spontaneous generation. Now on the flip side, if in a small region around a point there seems to be more fluid flowing into it than out of it, the divergence at that point would be a negative number. Remember, this vector field is really a function that takes in two-dimensional inputs and spits out two-dimensional outputs. The divergence of that vector field gives you a new function, one that takes in a single 2D point as its input, but its output depends on the behavior of the field in a small neighborhood around that point. In this way, it's analogous to a derivative, and that output is just a single number, measuring how much that point acts as a source or a sink. I'm purposefully delaying discussion of computations here. The understanding for what it represents is more important. Notice, this means that for an actual physical fluid, like water, rather than some imagined one used to illustrate an arbitrary vector field, then if that fluid is incompressible, the velocity vector field must have a divergence of 0 everywhere. That's an important constraint on what kinds of vector fields could solve real-world fluid flow problems. For the curl at a given point, you also think about the fluid flow around it, but this time, you ask how much that fluid tends to rotate around the point. As in, if you were to drop a twig in the fluid at that point, somehow fixing its center in place, would it tend to spin around? Regions where that rotation is counterclockwise are said to have positive curl, and regions where it's clockwise have negative curl. And it doesn't have to be that all of the vectors around the input are pointing counterclockwise or all of them are pointing clockwise. A point inside a region like this one, for example, would also have non-zero curl, since the flow is slow at the bottom but quick up top, resulting in a net clockwise influence. And really, true proper curl is a three-dimensional idea, one where you associate each point in 3D space with a new vector characterizing the rotation around that point according to a certain right-hand rule. And I have plenty of content from my time at Khan Academy describing this in more detail if you want. But for our main purpose, which is going to be showing the connection between these vector calculus ideas and complex analysis, I'll just be referring to the two-dimensional variant of curl, which associates each point in 2D space with a single number rather than a new vector. As I said, even though these intuitions are given in the context of fluid flow, both of these ideas are significant for other sorts of vector fields. One very important example is how electricity and magnetism are described by 4 special equations. These are known as Maxwell's equations, and they're written in the language of divergence and curl. This top one, for example, is Gauss's law, stating that the divergence of an electric field at a given point is proportional to the charge density at that point. Unpacking the intuition for this, you might imagine positively charged regions as acting like sources of some imagined fluid, and negatively charged regions as being the sinks of that fluid. And throughout parts of space where there is no charge, the fluid would be flowing incompressibly, just like water. Of course, there's not some literal electric fluid, but it's a very useful and a very pretty way to read an equation like this. Similarly, another important equation is that the divergence of the magnetic field is 0 everywhere. And you can understand that by saying that if the field represents a fluid flow, that fluid would be incompressible with no sources and no sinks. It acts just like water. This also has the interpretation that magnetic monopoles, something that acts just like a north or a south end of a magnet in isolation, don't exist. There's nothing analogous to positive and negative charges in an electric field. Likewise, the last two equations tell us that the way that one of these fields changes depends on the curl of the other field. And really, this is a purely three-dimensional idea, and a little outside of our main focus here. But the point is that divergence and curl arise in contexts that are unrelated to flow. And side note, the back and forth from these last two equations is what gives rise to light waves. And quite often, these ideas are useful in contexts which don't even seem spatial in nature at first. To take a classic example that students of differential equations often study, let's say that you wanted to track the population sizes of two different species, where maybe one of them is a predator of another. The state of this system at a given time, meaning the two population sizes, could be thought of as a point in two-dimensional space, what you would call the phase space of this system. For a given pair of population sizes, these populations may be inclined to change based on things like how reproductive are the two species, or just how much does one of them enjoy eating the other one. These rates of change would typically be written analytically as a set of differential equations. It's okay if you don't understand these particular equations. I'm just throwing them up for those of you who are curious, and because replacing variables with pictures makes me laugh a little bit. But the relevance here is that a nice way to visualize what such a set of equations is really saying is to associate each point on the plane, each pair of population sizes, with a vector.
Nur weil ich hier eben kurz diese Gleichung erklären will, beziehungsweise Hinweis nur geben will, dass diese Gleichungen im nächsten Semester Mathematik 3 angeguckt werden. Mathematik 3 ist, auch wenn Sie möglicherweise jetzt denken, dass das abstrakt wird und vielleicht noch schwieriger, eigentlich eine sehr schöne anschauliche Sache, weil wir in der Natur insgesamt immer Systeme betrachten, die sich verändern im Laufe der Zeit. Wie zum Beispiel Fuchs und Hase und das, was wir hier als Phasenraum gerade von ihm erklärt bekommen haben, heißt, wir können den Zustand eines Systems immer damit repräsentieren, dass wir sagen, wir haben einen Punkt, da haben wir dann so und so viel Hasen und so viel Füchse. Und wenn die Füchse dann entsprechend die Hasen weggefressen haben, dann gibt es zu wenig Hasen. Die Füchse haben dann nicht mehr genug Nahrung, haben dann schlechtere Überlebenschancen. Und wenn es weniger Füchse gibt, dann geht das sozusagen hier, dieser Fluss im Phasenraum, dieser Punkt bewegt sich dann wieder nach oben, so wie es dann gerade eben hier gezeigt hat. Das heißt, es gibt mehr Hasen und wenn wieder mehr Hasen da sind, haben wieder die Füchse mehr Nahrungsangebot. Und dies hier, das sind die Gleichungen dazu. Die zeitliche Änderung der Hasen, d Hase nach dt, und hier ist die zeitliche Änderung der Füchse oder der Fuchspopulation, und hier steht dann halt irgendeine Gleichung. Man kann diese Gleichungen auch verwenden in vielen anderen Bereichen. Es muss also nicht unbedingt um Fuchs und Hase gehen. Es gibt auch Gleichungen, die man aufstellt, zum Beispiel wie Beziehungen zwischen Mann und Frau ablaufen, wie Konflikte zwischen Staaten und Regierungen ablaufen, und die kann man auch mathematisch modellieren, bis hin zu solchen Epidemien, wie wir sie jetzt eine davon erleben. Die kann man auch mit solchen Differentialgleichungen modellieren. Also ich finde das jedenfalls eine sehr viel spannendere und interessantere Sache, als einfach nur irgendwo Parabeln zu malen und eine Kurvendiskussion zu machen. Wir lassen den Film jetzt noch ein bisschen laufen. Schauen Sie sich den bitte irgendwann mal ganz an und in Ruhe, und die 20 Minuten wollen wir jetzt hier nicht vollständig verschwenden darauf.
Indicating the rates of change for both variables. For example, when there are lots of foxes but relatively few rabbits, the number of foxes might tend to go down because of the constrained food supply, and the number of rabbits might also tend to go down because they're getting eaten by all of the foxes, potentially at a rate that's faster than they can reproduce. So a given vector here is telling you how, and how quickly, a given pair of population sizes tends to change. Notice, this is a case where the vector field is not about physical space, but instead it's a representation of a certain dynamic system that has two variables and how that system evolves over time. This can maybe also give a sense for why mathematicians care about studying the geometry of higher dimensions. What if our system was tracking more than just 2 or 3 numbers? Now the flow associated with this field is called the phase flow for our differential equation, and it's a way to conceptualize, at a glance, how many possible starting states would evolve over time. Operations like divergence and curl can help to inform you about the system. Do the population sizes tend to converge towards a particular pair of numbers? Or are there some values that they diverge away from? Are there cyclic patterns? And are those cycles stable or unstable? To be perfectly honest with you, for something like this, you'd often want to bring in related tools beyond just divergence and curl. Those would give you the full story. But the frame of mind that practice with these two ideas brings you carries over well to studying setups like this with similar pieces of mathematical machinery. Now, if you really want to get a handle on these ideas, you'd want to learn how to compute them and to practice those computations. And I'll leave some links to where you can learn about this and practice if you want. Again, I did some videos and articles and worked examples for Khan Academy on this topic during my time there.
Also dieser Mann, der hat vorher für eine Online-Firma gearbeitet, Khan Akademie, und dort eben auch schon Online-Kurse gemacht. Und den Rest, den wir jetzt hier sehen, auch die mathematische Beschreibung, haben wir eigentlich schon gemacht. Hier ist es nur für 2 Dimensionen aufgeschrieben. Also Divergenz haben wir ja schon gesehen, Nabla mal f. F ist eben dieses Vektorfeld, was wir untersuchen. Hat hier nur 2 Komponenten, ein Skalarprodukt. Und hier wird das gleiche Vektorfeld mit einem Kreuzprodukt mit Nabla multipliziert. Das ist das, was wir hier haben. Und wenn ich jetzt vorsichtig schaffe, vorzuspulen, sehen wir dann auch hier die entsprechenden Operationen, die man ausführen muss, um das zu berechnen. Wohlgemerkt im zweidimensionalen. Und hier auch nochmal sehr schön zu sehen, wie das aussieht, wenn wir dann eine Divergenz haben. Diese Divergenzen oder diese Wirbelrotationen werden eben für jeden Punkt im Raum berechnet. Also das ist sozusagen nur ein Beispiel und den Rest sparen wir uns jetzt erstmal. Sie sehen aber, hier sind viele interessante Sachen dabei. Ich mache das Fensterchen hier zu. Ich gehe wieder zurück, mache das VLC-Fenster zu und bin eigentlich mit diesem Foliensatz jetzt hier fertig. Ich habe hier nochmal eine Wiederholung vom letzten Semester, weil ich ja leider weiß, dass viele Sachen vergisst man immer. Das ist wie mit dem Vokabelnlernen auch, was ein Skalarprodukt ist, was ein Vektorprodukt ist und die 2 Arten von Vektorprodukten und was dabei herauskommt. Ich würde sagen, das schauen Sie sich einfach jetzt nochmal an. Das muss ich jetzt nicht nochmal hier wiederholen und erklären. Sie sehen auch, das Kreuzprodukt ist jetzt erklärt mit der rechten und linken Handregel.